So I just wanted to make a quick video to respond to a few questions I got by email. Um, so this question is one of the true-false questions from, I think, an old exam. We want to show that P implies Q and not R implies not Q logically implies P implies R. And the thing is, the person who sent this to me, I think it's clear from their email that they understand that it is possible to solve this problem if you take enough time and you do like a truth table or something like that. But um, on an exam, you don't have a lot of time to solve these true-false questions. So you want to have a quick way of seeing why this is true. So what I sort of want to do is instead of looking at this statement, so that, by the way, this is what we're trying to prove, or we're trying to determine if it's true or false. Let's think about the contrapositive, right? So I'm going to switch the two sides of the implication, and I'm going to negate them. Okay, and if you think about how De Morgan's works, then this becomes the negation. This is the contrapositive of the logical implication. Now, the reason I'm doing this is because the negation of an implication tells me a lot about the variables. So if not P implies R is true, then that tells me that P is true and R is false. Okay. And now, so if I'm assuming not P implies R, I get that P is true, R is false. And now I just think about, okay, what about Q? If Q is false, then P implies Q, because P is true, P implies Q becomes false. And so the first part of this this or statement becomes true because it's not true that P implies Q. And if Q is true, then because R is false, not R implies not Q becomes false. Okay. And so if Q is false or if Q is true, either way, the thing on the right-hand side is true. And so the implication is true. Okay. If you were on a test, you wouldn't write all of this because you're just trying to get whether it's true or false. But this is the explanation. Next question, it says if R is a symmetric intransitive relation on a non-empty set X, then R is reflexive. Now, this is not going to be true because, I mean, if it was true, then when we define equivalence relations, there would be no reason to say that it has to be reflexive, right? Because if symmetric intransitive implies reflexive, then we wouldn't need to say anything about reflexive. But the thing is, it's might be hard to come up with a counterexample to this because actually it kind of seems like symmetric intransitive would imply reflexive because, for example, if I have a B in R, then it will imply that BA is in R by symmetry, but then AB in R and BA in R implies that AA is in R by transitivity. And so like it feels like symmetric and transitive implies reflexive, but it doesn't. Okay, and here's the reason. Let's say I just let A be the set, or sorry, X is the set, I don't know, 1, 2, 3. And let's take R to be the relation just 1, 1, I don't know, 1, 2, 2, 1, 2, 2. And if you check, this is symmetric, it's transitive, but it's not reflexive because 3, 3 is not in the relation. So that's why symmetric intransitive does not imply reflexive, because there may be some element of x that is not even involved in the relation at all. Okay. Another example could be to just take x to be, any non-empty set and let R be the empty set. Okay, so these are two different examples which show that that it's not yeah, it shows that symmetric. These are two examples that show that symmetric intransitive does not imply reflexive. Okay, let's go back and do a question from set theory, because I know that a lot of you still find this quite difficult. So this is question 17/18 from section 3.15. We want to prove that the set difference of A and B union C is equal to A set difference B intersect A set difference C. And basically these questions ask us to do this in several different ways. Let me start with a proof by laws of set theory. Okay, so I'll just start by writing out what the set difference operation means in terms of intersections and complements. And my justification for this is that it's just a known set equality. Now, the next step is you can see that there's kind of a De Morgan's that is kind of staring at you here, right? I've got a union with a complement on the outside. So what I want to do is bring that inside. Okay, and that's, again, by De Morgan's law. And now, and now this is looking kind of okay, but it's not quite what we wanted. I need to do some shuffling around. And also, I need kind of two A's in this thing. So you can see in the final expression on the right-hand side, like if you think about what that's equivalent to, that's equal to A intersect B complement intersect A intersect C complement. So there's like two A's in that expression. It might not be obvious how to get that, but the thing is that A intersect A is just A. Okay, that's one of our known set equalities. So I'm going to use that right here, just to introduce another A into this expression. Okay, and here what I'm using is idempotence. Okay, you don't have to remember the word idempotence. So it's also okay in this case to say known set equality. Okay, now I want to reorganize the stuff, and I'm going to do that using two different things: associativity, which allows me to move brackets around, and commutativity, which allows me to change the order of sets within an intersection or a union. So everything here is an intersection. So using associativity and commutativity, I can reorganize it to get A intersect B complement intersect A intersect C complement. And my reasoning is associativity and commutativity. And then as my last step, I can just convert it into the thing I wanted. So it's A minus, or A set minus B, or set difference, intersect A set difference C, and that's by a known set equality times 2. Okay, so I started on one side of this equation and I got to the other side, so therefore these two sets are always equal. The question says to also do it using logical equivalences and set builder notation. Um, the thing is, though, that proof is the same thing. I'm gonna do the exact same thing, but with curly brackets and writing X as an element of A and stuff like that instead of just writing the set. I mean, so that proof is kind of the same. Let me show you another proof, which is not obviously like it's not quite the same thing. So let's do this by showing that the left-hand side is a subset of the right side, and the right side is a subset of the left side. Okay, because this is a very standard method that you need to know, and I think that a lot of people do struggle with doing this. So to do this, we start by letting X be an element of A set difference B union C. And then we just interpret this. So this means that X is in A and X is not in B union C. So always in a subset proof, you want to start by letting X be some element of the left-hand side, or the smaller of the two sets, or the thing that you want to show is a subset of the other one. And then we want to interpret this. And what does it mean for X to be an element of A set difference B union C? It means that X is in A and it's not in B union C. Okay, so what we can get from this is that, again, X is in A, and if X is not in the union of B and C, then it can't be in B, because then it would be in the union of B and C, and it also cannot be in C, because if it was in C, it would be in the union of B and C. So what we get is X is in A, it's not in B, and it's not in C. But now we can interpret this further and get that X is in A and X is not in B, and X is in A and X is not in C. Now you might be wondering, how did I know to do that, right? Why am I doing that? The reason I'm doing that is because I want to show that X is in the set on the right-hand side of this thing that I've got written at the top. And this statement I've got here is what that means. Okay, so that kind of guides me towards figuring out what to do at this step. So finally, what this tells me is that X is in A set difference B, and X is in A set difference C, so it's in the intersection of the two. Okay, so therefore, A is a subset, sorry, A set difference B union C is a subset of A set difference B intersect A set difference C. Okay, so to show that these sets are equal, though, we need to show the other direction as well. So maybe instead of me doing that for you, I'll just leave that one up to you, and you can think about it on your own. But basically, if you just sort of do what we did here and you kind of do it in reverse, that's going to be good enough to prove that. Yeah, here's another couple of questions that I received by email. One of them, kind of an interesting question. So you've got f is a function from the integers to the integers, and g is a function from the integers to the integers union the symbol smiley face. And they're defined in the following way. F of x is 2x and g of x is equal to 2x for all integers x. And the question is, are f and g equal sets? The important thing here is this word sets, okay? The answer is that yes, f and g are equal as sets. So they are the same set because f is the set of all pairs x, 2x, where x is an integer, and g is also the set of all pairs x, 2x, such that x is an integer. Okay, and you know, what does it mean for two sets to be equal, right? It means that they have the same elements. And so in this case, these sets have the same elements. So these sets have the same elements, and so they are equal as sets. Now, this can be a bit confusing because they are not the same function. Okay, and the reason that they're not the same function, they're not equal when you think of them as functions, is because they have different codomains. Okay, so this is kind of an unfortunate thing about functions, the fact that in some sense, a function is a set, but in another sense, they're kind of not treated the same way as sets because what it means for two functions to be equal is different than it is for sets. But so to answer your question, it's true that these functions are equal as sets, but they are not equal as functions. That's confusing, but don't blame the messenger. I don't choose the notation and terminology in mathematics. But this is technically what the answer is. The next question is about the definition of antisymmetry. Um, the question is kind of a theoretical one. So it's really asking, what does x equal y mean? So, because remember, the definition of antisymmetry means that if x is related to y and y is related to x, then x equals y. And the question is like, what do we mean by equals? And this is a good question because in some sense, the definition of equals is kind of supposed to be clear from context. So the thing is, x and y are some kind of mathematical objects. They could be numbers, they could be sets, they could be functions. And so when we say that x is equal to y, the meaning of that statement kind of depends on the context. So if x and y are numbers, it just means that they are the same number. So for example, 1 over 2 equals 2 over 4, right? If x and y were sets, then what it means for x to equal y is that they have the same elements. So we would use the equality definition for sets if they were sets. If x and y are functions, for example, we would say that they're equal as functions, which means they have the same domain, the same codomain, and every element of the domain has the same image under the two functions. Okay, so generally speaking, the equality in the definition of antisymmetry, it means basically whatever is the appropriate notion of equality for the types of objects that you're dealing with. A lot of the time, equality just means same, right? So if this is a relation on the set A, B, C, D, then what does it mean to have equality? It just means like A is equal to A, but A is not equal to B. So equality just means like is the same element. But yeah, that is a good question. And it doesn't have a really good answer, but basically equals means whatever it should mean in the context.